Okay, I guess I'll get started. Name? No. So, the chapter 21 homework will be due on Thursday, the 5th. The chapter 22 homework will be due a week later on the 12th. I think that's right. The chapter 21 quiz will be on Thursday the 5th. The report on Pangea, the lab report for Pangea is due today. If you need a little bit longer, let me know, we can talk, but it is due today. We will have another lab today on classifying rocks. So let's get moving with lecture. So we were discussing minerals. The largest and most common group of minerals is the silicates. The silicates are minerals that are made primarily of silicon and oxygen. And the pure, quartz, which is one of the very common mineral, is pure silicon and oxygen. It's made of silicon dioxide. It has the chemical formula SiO2. Most sand is just quartz. Quartz and other minerals that contain oxygen and silicon are called silicates. They are the most abundant rock-forming minerals in the crust. And I need to hit yes, because I didn't do that yet. So here's a short video about gems, minerals, crystals, and rocks, which should hopefully play.
What are minerals, rocks, crystals, and gems? What's the difference? Well, to start off simply, rocks, crystals, and gems all can be made up of minerals. So what the heck is a mineral? A mineral is a solid made by the natural activities of Earth, like lava spewing out of volcanoes or water dripping down through cracks in caves. Fluorite, gold, and calcite are just a few mineral names you might recognize. Minerals are made up of elements that come together in a regular, specific pattern. These geometric groups of elements are the building blocks of a mineral. A crystal of that mineral forms when these building blocks stack on top of one another, repeating their arrangement to form a three-dimensional object with flat faces. Quartz, for example, has a crystal structure made of oxygen atoms and silicon atoms that repeat in a shape that looks like a rhombus. The shapes that these chemical building blocks take are different from mineral to mineral. Sometimes, two minerals can be made of the same elements, but with different building blocks making up their structure, like diamond and graphite. The large geometric shapes and flat faces we see in crystals reflect what happens when these building blocks repeat over and over again. Now let's move on to rocks. A rock is a solid object made up of mineral grains, but it can have many different minerals inside it, and you don't see the same repetitive shapes that you see in crystals. Granite is an easy example. You can see the different grains of many types of minerals making up a piece. Limestone is also a rock, even though it's usually made of mostly one mineral, calcite. But limestone is made of calcite fragments mashed all together, and a calcite crystal has order and a geometric shape. So where do gems fit in? They have a geometric shape, and many look like crystals, right? But really, gems are minerals or stones that have been cut, ground, and polished by people to enhance their beauty. A finished gem may look very different from the original mineral it was carved from. Many times, gems are shaped with different flat faces to catch and scatter light. They aren't always minerals either. They can be made of things that come from animals and plants, like pearls or amber, or they might even be man-made in a lab. Let's make like a crystal and repeat that one more time. Think about pyrite or fool's gold. Pyrite is a mineral made of iron and sulfur. Those elements come together in the shape of a cube and repeat to form a pyrite crystal. These crystals can get so big you can see them with your naked eye. Other times, the pyrite crystals are just flecks in a rock like slate. And if it was cut and polished with flat faces, it would be considered a pyrite gem. So there you have it, crystal clear. The difference between minerals, gems, rocks, and crystals.
So, silicates. The structure of silicates is based on this silicate SiO4 tetrahedron. Basically, the general way that these organize together is that you get an oxygen surrounded by, you get a silicon surrounded by 4 oxygens, and then these tetrahedrons can combine. So this silicon oxygen tetrahedron. You can have covalent bonding within the tetrahedron between the silicons and the oxygens. The tetrahedron can share oxygens. So if all the oxygens are shared with nearby tetrahedra and there isn't anything else, you get quartz. But there's a whole bunch of different ways these tetrahedra can be organized. And a significant amount of variation occurs in the structural arrangement of the tetrahedra, and these correspond to different minerals. So the silicon oxygen tetrahedron can exist independently. There's no sharing of oxygen, or they may share oxygens in various ways. So here's the basic building block, the silicon oxygen tetrahedron. And these can combine to form a complicated 3D structure like in quartz or feldspar. They can form sheets like in various micas. They can form chains, either single or double chains. They can exist just independently with other ions. So in addition to oxygen and silicon, most silicon minerals also contain aluminum and 1 or more other elements. And the various silicon minerals result from the different structural arrangement of the silicon oxygen tetrahedron building blocks and the different metal ions within these structures. So you can have aluminum, you can have magnesium, you can have iron, you can have sodium, you can have potassium, things like that. And the silicon oxygen tetrahedron can be arranged independently in single chains, in double chains, as continuous sheets, and as a 3-dimensional network. I think you can have single silicon tetrahedra with other ions around, chains, either single or double chains, continuous sheets, or a 3D network. And the 3D network can have other ions or no other ions. With other ions, you get feldspar. With nothing else, you get quartz. So the most common silicate group of minerals is the feldspars. They're structurally related. They have a 3-dimensional network. And they're a set of the most abundant minerals in the Earth's crust. And there's 2 basic types. There are plagioclase feldspars, which have oxygen, silicon, aluminum, and either calcium or sodium. And potassium feldspars, which have oxygen, silicon, aluminum, and potassium. So all silicates have oxygen and silicon. The other added metals vary. So here's a sodium-rich feldspar, which is albite. Here's anthracite, which is a calcium-rich feldspar. And here's some other silicate minerals. So here's a feldspar. Here's olivine. Olivine has a lot of iron and magnesium, and I think is single silicate tetrahedra. Here's quartz. Here's mica. Micas have those flat sheets of silicon. So they're very strong along the direction of the sheets, but weak the other way. So you can peel off thin layers of mica, which makes them useful. And then pyroxene, which I don't remember its structure off the top of my head. Now, all the other minerals in the crust are considered non-silicate. So the most common type is silicate, everything else non-silicate. Now, these comprise less than 10% of the minerals in the crust. They're probably a bit more at the surface because one of the common non-silicate minerals is very common in sedimentary rock, which tends to cover the surface. These are carbonates, oxides, and sulfides are the most common non-silicate minerals. There are others. So like gold is a non-silicate mineral. Diamond is a non-silicate mineral. But I guess diamond is probably argued. Well, no, it's not a carbonate. There are other ones that are not on here. There's also sulfates as well as sulfides. And then pure elements like gold and silver. There's some gemstones. Diamond, ruby, and sapphire are all non-silicates. Diamond is pure carbon. Ruby and sapphire are actually both the same mineral, corundum, which is aluminum oxide. If you have a piece of aluminum, there's a very thin layer of aluminum oxide on it because it reacts with the oxygen in the air. Part of why aluminum doesn't interact with a lot of stuff. It's because it reacts so quickly that it passivates itself. It doesn't rust because it actually protective layer. So carbonates are minerals with the carbonate ion, which is CO3 2 minus, and when it bonds with various other metal ions. So the most common, most well-known carbonate is calcium carbonate, which is the main ingredient in limestone. It's what limestone is basically made of. It's what seashells are also made of. Lots of other things. So calcium carbonate is a very common carbonate mineral, but you can have iron carbonate, magnesium carbonate, manganese carbonate? I don't remember what Mn is. So calcite is the primary mineral component of the rock limestone. So and because of this is actually why limestone forms caves, because calcite is soluble in mild acids, and groundwater is slightly acidic. So limestone will dissolve over time in the slightly acidic groundwaters, and that'll contribute to cave formation. So one of the ways you can test if something is calcite is actually put a drop of acid on it. It will bubble up because it will release carbon dioxide as it reacts with the acid. Like, you ever mix baking soda and vinegar? Baking soda is sodium bicarbonate. It's got 2 carbonates. So it really bubbles up. But when a carbonate ion interacts with an acid, it becomes carbon dioxide. And so it releases it as gas. Now, oxide minerals form through the bonding of oxygen ions with metallic ions. So there's lots of oxides. So there's a number of different iron oxides. So this is Fe2O3. And there's, I think that's thing type, but I could be remembering wrong because there's a bunch of different iron oxides. There's SiO2, that's tin oxide, and uranium oxide, tin dioxide, and uranium dioxide. These are all oxide ores for their respective metallic ion. You've probably seen iron oxide. You just called it rust. Rust is iron oxide. That's also where a lot of red rocks are red because they contain red iron oxides in them. That's one of the common ways that rocks become red. So oxide ores are very common for various metals because oxygen reacts with lots of stuff. So lots of useful ores are often oxides. Not all. There are also sulfide minerals. These form from the bonding of sulfur ions with metallic ions. So iron, lead, copper, zinc, and others can bond with sulfur. So iron FeS2 is pyrite. That's commonly known as fool's gold. And CuF, copper iron sulfide, lead sulfide, and zinc sulfide are all sulfide ores for the respective metallic ion. Lead sulfide is called galena. There's a town in Western Illinois called Galena, named after the mineral, because there are lead mines there. There were lead mines there. They were digging up galena to extract the lead. But there's also, if you've heard of vermilion or what's the other name for it? Mercury sulfide is very dramatic red color. So it was used traditionally in red, like paints and things. I can't remember the other name for it. But you can form gemstones from it. So here's pyrite, which is lead sulfide. Here's uranium dioxide. That's the ore for uranium. And in fact, in a lot of places when we're using uranium, we keep it as uranium dioxide. So like nuclear power plants, you don't need a concentration of uranium that's super, super high. So actually the fuel for nuclear power plants is made from uranium dioxide. That's been concentrated up to have more U250, U265. I can't remember the number off the top of my head. The one that undergoes fission. And then carbonate. This is limestone. So calcite, calcium carbonate is the primary component of the limestone. Now, to identify minerals, we can do this based on physical and chemical properties. And this is advantageous because there's some minerals that have the same chemical formula, but different molecular structures. The most dramatic example that gets used a lot for this is graphite and diamond have the same chemical formula. They're both made of pure carbon. But they have dramatically different minerals because they have very different crystal structures. Graphite forms in flat sheets, which easily can be flake off. Diamond is a three-dimensional structure, so it ends up being hard, clear, and crystalline, while pure graphite is soft and black. We use it as a lubricant. It's, what you write with when you're using pencil lead. The pencil lead is actually a mixture of graphite and clay to hold the bits of graphite together and make it write out better. But I mean, you can just take a chunk of graphite, you can write with it. It works. But to get a better writing experience, they mix it with clay. But here's the difference. Diamond has a complex three-dimensional structure full of covalent bonds. Graphite is made of sheets covalently bonded together with very weak binding forces between those layers and sheets. And if you've heard of graphene, graphene is a single one of these graphite sheets. That is what graphene is. So you can identify minerals by careful and costly chemical analysis, various things like that. But a lot of the time you can identify them just by looking at their distinctive physical properties. Because they form crystals of certain shapes and they have certain properties, and these are pretty straightforward to learn and are known by any serious rock and mineral collector. And a particular physical property that identifies one mineral may not help with another. So the key is to find which property identifies which mineral. So there's some good discussion of this in the anime I mentioned, Worry Rocks, where they because the main character in that is looking for gemstones specifically because she wants pretty shiny rocks, which is something I can totally understand, and is looking for them out in the wild, and so is learning about how to identify various minerals. So, certain physical properties that can be useful. The shape that crystals form in. The outward form of a crystal is a visible representation of the internal molecular structure. If a crystal has had a chance to grow freely, it will form a structure that is dictated by the internal structure that its atoms are arranged in. So many minerals have very characteristic crystal forms. Like quartz forms these pointy pillar things. And if crystallization occurs in an unrestricted space with just the right components and the right pressure and time conditions, you get a perfect crystal. This is very rare, but there's often a portion of the crystal that you can look at and identify. So usually you have some sort of aggregate of crystals form with none of them exhibiting perfect crystal form, but you can see the underlying normal structure of the crystals. They're usually just stuck into each other. Because the problem is, as a crystal grows, if it runs into something, it's going to stop. And that can affect its shape. So some examples of some really dramatic crystals that have had a chance to grow under very good conditions are these in the Crystal Cave in Mexico. Don't remember off the top of my head exactly where in Mexico.
Deep beneath the earth in Chihuahua, Mexico,
Chihuahua,
grows a real-world fortress of solitude. In 1910, in the Nica mine in Mexico, the Penoles Mining Company discovered what came to be known as the Cave of Swords. It was an 80-meter-long hallway with beautiful gypsum crystals growing up to 2 meters in length. Unfortunately, the cave was opened up for exploration and later tourism, which destroyed many of the crystals. 90 years later, 2 miners working for the same company stumbled on another cave, except this one was much, much bigger. Nica sits on an ancient fault line above a magma chamber. This heated the groundwater and filled it with sulfide ions. So when this hot sulfide brew met with the cool oxygenated water in the cave, they didn't mix exactly, they kind of sat on top of each other, but the oxygen began to diffuse into this rich sulfide soup, and slowly, at an infinitesimal pace, these crystals began to form. They have been growing for 500,000 years. Today, the largest crystal in the cave is 12 meters in length, 4 meters in diameter, and 55 tons. It is 20 times bigger than any previously known crystal. Amazingly, there's no limit to how big these crystals can get. Given enough time, they will grow ever larger. These are Fortress of Solitude crystals. They are Superman crystals. One big difference between the Fortress of Solitude and the Cave of Crystals is the temperature. The Cave of Crystals is blisteringly hot. It is 50 degrees Celsius or 122 Fahrenheit, and the humidity level is a constant 90%. Even wearing special cooling suits filled with ice and water, researchers were only able to spend about 40 minutes down there. These crystals grew underwater. It's only in the last 20 years this mining company has pumped out all of the groundwater so they can extract various precious ores from the area. But as soon as it doesn't make economic sense for this mining company, the crystals will be resubmerged, returned to their underwater existence. And this is probably for the best. Because while it's incredible we get the chance to study them now, that's their natural environment, it's where they grew, it's where they can keep growing. And I think considering how beautiful, but also how fragile these are, just knowing that they're under your feet, growing ever larger, is more than enough. Subscribe here and watch more videos here. This isn't gypsum, this is salt. The NICA project is doing a ton of amazing science around this, including looking at ancient life forms in these crystals and trying to find their closest relative. I've included a link down below if you're interested in learning more about that.
So I believe that cave of crystals has been reflooded because the video is kind of old. But as time passed, it stopped being viable to continue mining there. They stopped pumping the water out, so it reflooded. So those crystals are now growing even bigger. Now, one of the things that you might think would be a great way to identify minerals is color. This is because we are visual beings. We like to identify things by color. However, color is actually a pretty lousy way to identify minerals. All three of these are the same mineral. This is citrine, this is amethyst, this is quartz. They're all quartz. The only difference is very small amounts of impurities in them. And amusingly, a lot of citrine that you can find to buy these days is apparently amethyst that has been treated to become that color. Which is unfortunate because I think the amethyst is much prettier. And fake citrine doesn't look as good as natural citrine. But this is citrine, amethyst, and quartz. They're all just variants of quartz with different impurities. It turns out very small amounts of impurities can create pretty big differences in what you see as color. So for example, rubies and sapphires are the same mineral. They're both corundum. Rubies have chromium in them, which makes them red. Sapphires have other things in them, which makes them various colors, because sapphire is a more general term, but the traditional ones are blue. I don't remember off the top of my head what impurity makes them blue. But you know what another thing that is also corundum is? Have you ever used an emery board to work on your nails? Emery on the emery boards, which is black, is corundum. It's not valuable corundum because it doesn't form large crystals and it's got iron impurities that make it a solid black, but it is corundum. We put corundum on sandpaper. If you've ever bought aluminum oxide sandpaper, that's chemically the same. It might not technically be the mineral because it might be artificially created. I don't know. But yeah, comes in lots of different colors. So, but some properties are useful. So color is not the best, but other physical properties are quite useful. Hardness is a good way to identify minerals. So it's the mineral's resistance to scratching or abrasion. The scale that's used primarily, there are absolute scales to measure hardness. When we're identifying minerals, they're not used very often. There is a relative scale that compares various minerals to other minerals or substances that is used primarily as the way for identifying different minerals. That's because comparing to other minerals and other substances in a way that doesn't correspond directly to the absolute hardness is just a lot more practical. Because, for example, the very hard minerals vary a lot in absolute hardness, but there's not a lot of minerals in between. So there's no point for having a lot of empty space on the scale, for example. So like the hardest mineral in existence is a whole lot harder than the second hardest. But there's no reason to leave a whole bunch of empty space. Now, there are absolute hardness scales. They tend to be used more in metallurgy. You know, how hard did I make my knife blade? Less in identifying minerals. Cleavage is the way that minerals break. So some minerals break along specific planes. And the way that they break forms, you see distinct planes that they break along. These represent planes in the crystal structure where the bonds are the weakest. These planes tell you something about the internal structure of the mineral. And so the cleavage you see can help you identify. For example, micas will peel off in thin sheets, showing one plane of cleavage. So here is an example of mica cleavage. You can peel off thin sheets because it is weak along one plane and strong along the others. The mineral splits along definite planes. When you get cleavage can occur, you can have one plane of cleavage, 2, 3, even 4 planes of cleavage, and then they could be at right angles or not at right angles. There's also fracture, which is when a mineral doesn't break along a nice plane. So you can either have rough, irregular, and there are different types of fracture. You can have a fracture that just looks irregular, like you'd normally think, oh, this is the edge of a rock. Or you can have these arc-like colloid fractures that are sort of shell-shaped. Those also can happen. This happens when, because of the tightly bonded atoms of the mineral. So this is like flint will break like this. Now hardness is measured on what's called the Mohs hardness scale. This is not an absolute hardness scale. If you plotted the Mohs hardness scale against absolute hardness, it would look like 1, 2, 3, 4, and then big jumps at the head. But there's not a lot of minerals in there, so this relative scale works great. The general rule, things that are higher on the Mohs hardness scale scratch things that are lower on the Mohs hardness scale. And that's how you test things. You try and scratch them, or you try and scratch things with them. So the hardest mineral is diamond. It is a 10 on the Mohs hardness scale. The softest mineral is talc. It is a 1 on the Mohs hardness scale. There are softer things like metallic sodium is a 0.5. But metallic sodium doesn't exist naturally in the world, in the environment. The next hardest mineral is corundum. That's like rubies and sapphires. That's a 9. Topaz and emerald are an 8. Zircons are 7.5. Quartz is a 7. Ceramic tile is a 7. You're likely to have a ceramic tile because there's a ceramic tile that is used for another form of mineral identification. So in the field, that's a very useful random thing to check. A steel file is around 6.5. Orphoclase or potassium feldspar is a 6. Glass is somewhere in the 5 to 6 range. So something like these feldspars are sort of the primary component of like granite. So quartz is harder than most granites. Apatite is a 5, as is tooth enamel. Platinum is 4.3. Fluorite is a 4, like iron or nickel. And an actual like nail is a little harder. A copper penny is 3.5. Calcite is a 3. Gold is 2.8. A human fingernail is 2.5. That's a good reference. Gypsum is a 2. So those giant crystals were made of gypsum. Drywall is also made of gypsum. So gypsum, that's probably what they're extracting in that mine. So gypsum is something that is mined for use in construction. Lead is about 1.5, and then talc is a 1. So when minerals break in an irregular manner, that's called fracture. Minerals that don't cleave, they don't have any planes of weakness in their structure, therefore they don't break in a uniform manner. But they can break in a couple different ways. They can be like sort of jagged and irregular, or they can form those smooth arcs. And that can help you differentiate between different minerals. And then color. So color is the property of reflecting a particular light wavelength. This is probably the first thing you notice. It's not usually reliable because lots of minerals that exist have many different colors. Because it turns out you only need a very small amount of impurities to change the color of a mineral. So quartz, for example, occurs in many colors, including clear, milky, smoky, yellow, purple, red, orange, pink, blue, green. Blue is not going to be green, brown. There are quartz crystals that vary in color throughout the crystal. They exist. There's some really cool quartz growths that have they kind of look like grass on dirt because they're like green going into brown. So yeah, they can vary quite a bit. And sometimes specific colors of a certain mineral will have a special name, even though they're the same mineral, like ruby and sapphire and emery are all corundum. They're all the same mineral, but they have different impurities. Now, one of the more useful ways to identify minerals based on color is actually streak. Streak is the color of the powder left behind by a mineral. So the color of a mineral in its powder form. And that is not necessarily going to be the same as the color of the mineral. So an intact mineral sample may exhibit several colors. The streak color will pretty much always be the same. You may have heard the term a touchstone. A touchstone originally was a way to check if the metal you had, like the precious metal, gold or silver, was real or its purity by checking its streak. Because real gold, leaves behind a gold colored streak. So you'd have a stone that you would rub a known good sample of gold and the gold that you were being offered on and compare them. And that was a touchstone. So an example of something where the streak is very different in color from the actual mineral is pyrite. Pyrite, you have a piece of pyrite, it's called fool's gold for a reason. It's yellow and shiny. The streak of pyrite is black or dark brown. Another factor that can be quite useful is luster, how a mineral's surface reflects light. So luster can be qualified in a lot of ways, but the main ways are either metallic or non-metallic. Metallic lusters look like metals. They're shiny and reflective. They look like polished metal. Non-metallic lusters can be things like vitreous or glassy, adamantine like diamond, pearly like opal, greasy like talc, or earthy and dull like clay. There's a bunch of non-metallic lusters out there. But here is an example of hematite. These are both hematite. You can see one is redder, one is blacker, but they both have a red-brown streak that looks almost the same. Turns out when you powder a mineral, and the way you do that is just rub it on this ceramic streak plate, which is a rough ceramic plate that will extract some powder as you scrape the rock against it, and you can compare the color there. You do that with pyrite, you get a black streak. So here is pyrite, it has a metallic luster, while limonite here has a non-metallic luster. They're both yellow, but pyrite is metallic and limonite is not. Also, pyrite has square crystals and such. Another thing that's very useful for identifying minerals, density. Different minerals have different densities. So if you can measure the density or specific gravity, as it will often be called, which is just density as compared to water, which is just density in grams per cubic centimeter, that's very useful. So specific gravity, the ratio of a mineral's weight to the weight of an equal volume of pure water, which is just, that is density in grams per milliliter or grams per cubic centimeter. It's just density. It means you can write it without units because you're comparing it to water. So lots of minerals have specific gravities between 3 and 4, 3 to 4 times as heavy as water. Some minerals are significantly higher. So galena Lead sulfide has a specific gravity of 7.6 because lead is heavy. Pure gold is probably the densest mineral you'll encounter. It has a specific gravity of 19.3. And there are other things that you might be able to identify minerals with. One of them is fluorescence. So here's a short video about fluorescence in minerals. If you'd like to see a display of fluorescent minerals, the Field Museum has a display of various fluorescent minerals. So some minerals glow. Fluorescence or phosphorescence?
Hello, my name is Deborah Wilson. I'm the collection manager for the section of minerals here at Carnegie Museum of Natural History. Today I'm going to show you an interesting hyalite opal. Most hyalite is very fluorescent, which means under ultraviolet light it'll glow. I've actually pulled a couple of samples of fluorite, and fluorite was the first mineral species that fluorescence was discovered in, so it was named after the fluorite. Certain specimens will have what we call activator elements in them that when the ultraviolet light is shining on it, it kind of excites the electrons and they move up to a higher state, and as they're moving back down, you'll see the light in your visible spectrum. There are two specimens of fluorite from England. You'll notice that they are different colors in natural light, but you'll see when we put them under the ultraviolet light that they fluoresce almost the same identical color. This is a vug, is what we call kind of an opening in the rock where these minerals are growing. There's little quartz crystals and chalcedony, which is a variety of quartz, that have a coating of hyalite opal on them. And this is from the Candelaria mine in Sonora, Mexico. So let's take a look and see what this hyalite opal looks like under the UV. This is shortwave ultraviolet, which most species that fluoresce do the best under shortwave. Some things will also fluoresce under long wave. Some will do either one or the other. Hyalite normally does shortwave, but we'll take you up to Hillman Hall and show you hyalite opal that actually fluoresces under long wave. So if I have a little ultraviolet pen, it'll penetrate the plexiglass and will actually make this fluoresce. Now this one also is so highly fluorescent, it will start glowing under natural sunlight. This deposit of hyalite opal was discovered in Zacatecas, Mexico in 2013, and it's all been mined out. There's no more coming out. This piece of rough is got little globular growths, it looks like, that you'll be able to see better when I make it fluoresce. And this gemstone is the second largest stone that was cut from everything that was recovered there. So let me show you how it fluoresces. Turns this bright green. You can see it a lot better on the matrix, and even the gemstone just pops when you hit it with the UV light.
If you like this video, please press like and subscribe. And also, please visit us here at the Carnegie Museum of Natural History.
So fluorescence is a phenomenon that happens with many different chemicals. It's in fact what is producing the light in this room right now. The fluorescent lights above us generate UV light, which hits a powder coating the inside of the fluorescent tube, which fluoresces white light. It's been chemically formulated so that it produces a bunch of different colors of light that we see as white. So there's also phosphorescence, which is when it absorbs light and then releases it later. That's, glow in the dark. You ever had something that's glow in the dark? That's, I think, technically phosphorescence. But fluorescence is more useful as a way to identify things, because you just shine a UV light on it and then it will emit a specific color. It's useful not just for identifying minerals. Another use for fluorescence is that it's really great, for example, finding scorpions, because all scorpions fluoresce. As do a surprising number of mammals, which was an odd thing. But yeah, so here are some examples of things that you can use to identify minerals. The size and shape of the crystal faces. Is it a tetrahedron, a rhombohedron, etc.? The hardness, the ability to resist scratches. We use the Mohs hardness scale, which is a scale from 1 to 10. There are other hardness scales out there, some of which are actual like direct measurements of hardness. But while the Mohs hardness scale is just a relative scale, but it is by far the most useful for identifying minerals because it covers a really nice range and it's distributed based on basically how common minerals are at various hardnesses. There's cleavage, which is the tendency to break along definite smooth planes. There's fracture, which is the way that the mineral breaks. Does it splinter, form irregular pieces, or shell-shaped forms? There's the color, which can be useful, but also often the same mineral can have lots of different colors. There's streak, which is much better for identifying, which is the color of the powder of the mineral, which is usually found by rubbing it against a streak plate, leaving behind a streak. There is luster, which is the surface appearance in reflected light. Is it metallic? Is it non-metallic? And then there's specific gravity, which is the ratio of the sample mass to a mass of an equal volume of water, i.e. density. It's a measure of density. Now, a rock is a natural solid cohesive aggregate of one or more minerals. Technically, rocks can contain some things that aren't minerals and still be considered a rock, just because there are some naturally occurring non-mineral things we'd like to consider rocks, like obsidian or coal. These are called mineraloids, but that's just a technicality. Primarily, rocks are made of minerals. The rocks are mixtures of minerals, while minerals are composed of individual elements or compounds with specific chemical formulas. You can have a rock that's made of just one mineral, but most rocks are made of several. And different types of rock comprise the vast majority of the Earth's crust. In general, when we look at a rock, we don't see the individual minerals. We see sort of the aggregate. And rocks can be divided into three major types as a result of the way they formed. There are igneous rocks, which formed from molten rock. Igneous means born of fire. There are sedimentary rocks, which formed from sediment, broken down little pieces of rock in various ways. So they're sedimentary. And there are metamorphic rocks, which are rocks that were some other rock that were changed by heat and pressure and transformed into a different type of rock. So igneous rocks are a rock formed from molten material that's cooled and solidified. And molten rock is either magma when it's underground. So molten rock material that originates deep within the earth is magma. And rocks that solidify from magma beneath the Earth's surface are called intrusive igneous rocks. And then if magma reaches the surface and exits, it becomes lava. That's the only difference between magma and lava. Magma's underground, lava's on the surface. So lava is molten rock material that reaches the Earth's surface due to volcanic eruption, and rocks that solidify from lava at the surface are called extrusive igneous rocks. Intrusive igneous rocks are inside the Earth. Extrusive igneous rocks are external to the Earth. So here are some extrusive igneous rocks. This is a piece of basalt formed from lava. This is cooled lava. This is like, this is poke lava, I think. I'm mispronouncing it because it's a Hawaiian term and I'm no good at speaking going like this.
Does obsidian fall into one of those three categories?
It's an extrusive igneous rock.
Yeah, I figured.
It's a very fast cooling extrusive igneous rock. So the main difference between intrusive and igneous is how long they take to crystallize. Obsidian is at the far, so, intrusive igneous rocks are slow, extrusive igneous rocks are fast. Obsidian is super fast. Here's an intrusive igneous rock. So you can see here the crystals are really small in this rock because it cooled very fast. Here, this is granite. You can see the crystals are much larger because it cooled more slowly. Obsidian is the point where it cooled so fast no crystals formed at all. Now, sedimentary rocks are rocks that form at or right near the surface of the earth due to the compacting and cementation of sediments. So basically, you have bits of broken rock material. They collect, they get compacted by the weight of all the material above them, and then they get cemented together, glued together by dissolved minerals. So the sediments that comprise sedimentary rocks come from three general sources: rock fragments due to the erosion of pre-existing older rocks, minerals chemically precipitated from solution, so dissolved minerals precipitating out, and plant or animal remains, fossils. So sedimentary rock is the primary place you'll find fossils. So for example, here as a sedimentary rock, here is sandstone. You take a bunch of sand, you compress it, and you allow dissolved minerals to glue it together. You get sandstone. Metamorphic rocks are rocks formed by taking some existing rock, putting them under conditions of high pressure and temperature, and they transform into a new type of rock. So they're formed on the alteration of a pre-existing rock due to the effects of pressure, high temperature, and or a chemical change. Metamorphism usually occurs well below the surface of the earth, but at shallower depths and at temperatures that would cause the rock to melt. So it's not getting hot enough to melt, but it is getting hot enough to chemically change. So here is a sample of schist, which is a metamorphic rock that forms from several different rocks. And there's a process, so you can have more and less metamorphized rocks. So this is a pretty heavily metamorphized rock. And there are metamorphic rocks that are less metamorphized, sort of on the chain, leading to that. Now, one of the principles of modern geology that helps us understand the world we live in is uniformitarianism, which is an awful word to try and remember and say. But uniformitarianism is basically this idea that was put forth by the Scottish precision scientist James Hutton, who spent a lot of time wandering around Scotland, which has a lot of exposed geology, because he started to realize that ancient rocks were formed in the same way as modern rocks. And because they're formed in the same way, they can be interpreted similarly. So basically, uniformitarianism says that the geologic processes we see happening today also happened in the past. So the rocks formed by the processes we see happening today, if we see them old rocks buried deep underground, well, that means they were formed in the way we're seeing them formed today. So basically, the present is the key to the past. So geologic processes occurring today operated similarly in the past, and they can therefore be used to explain past geologic events. So most rocks that we find, the process that forms them still occurs somewhere on Earth. We can observe that and say, okay, that process was happening millions of years ago when these rocks formed. There are exceptions. So, for example, there are certain types of rocks that just don't form anymore because the conditions that caused them to form don't exist on Earth anymore. Amusingly, the most common iron ore we use today, the process that forms it doesn't happen anymore because the biosphere of the Earth has changed. But the general idea of uniformitarianism is that the present, what we see happening today, is the key to understanding what happened in the past. And James Hutton was also the person who recognized that rocks in the Earth's crust were continually being formed, broken down, and reformed. They're constantly being reprocessed. And these are the same processes responsible for forming the three types of rocks: igneous, sedimentary, and metamorphic. And this process is called the rock cycle. So this model of continuous cycling of crustal rock material is called the rock cycle. And the rock cycle is sort of the series of events by which rocks cycle between various types and can go from one form to another. So rocks will change over time between igneous, sedimentary, and metamorphic forms. The rock cycle is commonly expressed in a way where it's going igneous, sedimentary, metamorphic, and then back to igneous. But it doesn't have to go that way. Basically, any form of rock can turn into any other form of rock. So processes within the rock cycle include things like deposition, transportation, weathering. So deposition is, laying down of sediment. Transportation is moving sediment. Weathering is the breaking of a rock into little pieces. Melting of a rock, crystallization, which is sort of the opposite of melting. Cementation, compaction, etc. So here's sort of a simplified view of the rock cycle. It's got some extra arrows to give you an idea. Magma cools and solidifies and crystallizes to form igneous rock that can weather and erode to form sediment, which will compact and cement to form sedimentary rock. But any rock can weather and erode to form sediment, and then compact and cement to form sedimentary rock. Then heat and pressure on sedimentary rock can metamorphose it to metamorphic rock. But heat and pressure on igneous rock can metamorph it to form metamorphic rock as well. And then any rock can melt to form magma and reform igneous rock. So it is more common with metamorphic and igneous rock than sedimentary rock, just because they tend to be deeper underground. Sedimentary rock is less likely to be pushed underground and melt. But it does happen. So Hutton also recognized that the processes that form and break down the different rock types take enormous amounts of time. And thus he hypothesized the Earth to be very old. And so central to the science of geology are these following three concepts. This principle of uniformitarianism, what we see today, informs us as to what occurred in the past. The rock cycle, the cycle of rocks changing from one form into another, and the recognition that the Earth is very old. The Earth is about 4.5 to 5 billion years old. It's quite old. Now, the energy for the rock cycle comes from two main sources. For igneous and metamorphic rocks, the heat and pressure that forms them comes from plate tectonics, driven by heat from within the Earth. But weathering, the process of weathering, which is what creates sedimentary rocks, that is primarily driven by energy from the sun. Because it has to do with often heat cold cycles, plants, water dissolving things. The movement of all those materials tends to be driven by energy from the sun. So here's a video about the rock cycle.
Okay, let's take a quick look at the rock cycle. Here's a diagram showing the rock cycle in the Earth's crust. This particular diagram can be found in the New York State Earth Science reference tables. What it shows are the different types of rocks and how they can change over time. Let's go through a quick example. Here is a chunk of an igneous rock known as granite. You can see it's made up of intergrown crystals of potassium feldspar and quartz and biotite, and that's what gives it its speckled look. Now, as we mentioned, granite's an igneous rock, which forms from the solidification of melted material, magma or lava. granite happens to form deep underground from the slow cooling of magma. But the question we want to look at now is, well, what can happen to this igneous rock over time? And there's a handful of possibilities. The first thing that could happen is our granite could be lifted up, forced up from beneath the ground where it's exposed to weathering and erosion. The wind, the rain, the ice, these forces break this rock down into little small pieces called sediments. So now our granite has been broken into small pieces of granite. Now these little small sediments can be deposited and buried and then compacted and cemented together to form a brand new rock called a sedimentary rock, like this piece of sandstone. So simply by weathering and eroding the granite into sediments and then squeezing the sediments back together, you've converted your igneous rock into a sedimentary rock. But that's not the only thing that can happen to our igneous rock. What if it is pushed even deeper underground by the movement of Earth's tectonic plates, and in so it is exposed to intense heat and or pressure, causing it to metamorphose or recrystallize into a metamorphic rock, like this piece of gneiss seen here. So, with the simple addition of some heat and pressure, we've turned our igneous rock into a metamorphic rock. But there's still one more option. What if our igneous rock is exposed to intense heat, causing it to melt and return into liquid state of magma? Well, it can then, of course, cool and solidify again, giving us another igneous rock. But maybe this time it will cool quickly and give us something with smaller crystals or maybe no crystals at all, like this piece of obsidian. So what you can see is that on the rock cycle, any rock is able to turn into any other rock when exposed to the different processes in and on the Earth's surface. Remember, we start with these three types of rocks. These are our three classifications. And from them, we can go to anything else. Again, let's look at the igneous rock, right? Igneous rock, we know, forms from melting into magma and solidification. But remember, it can melt again, and that process can happen over and over and over again. So I can have an igneous rock that becomes igneous again, maybe a different kind of igneous rock. But any rock can melt into magma and form an igneous rock, as seen on the chart. Sedimentary, metamorphic rocks, they can all be melted and ultimately result in an igneous rock forming. Well, let's look at the sedimentary rock. Now remember, these form from sediments that have been deposited and buried and pressure causing them to compact and cement together. But of course, any rock can be weathered into sediments, and therefore any metamorphic or igneous rock can become a sedimentary rock. Finally, we have our metamorphic rock, and remember, these form when rocks are exposed to intense heat and pressure. But of course, that process can take place with any type of rock, sedimentary, igneous, or even metamorphic rocks. So the key idea behind the rock cycle is the fact that any rock can become any other kind of rock. It can even become itself. Change is always taking place. It's generally slow over many millions of years. However, the results can be impressive. Thanks.
So, igneous rocks form from the solidification of molten material that generally originates far beneath the surface of the Earth. If that material is underground, it is called magma. When it reaches the surface, it is called lava. So the difference between magma and lava is just one is underground, one's on the surface. The term lava is also used to describe the resulting and cooled igneous rock. We talk about like lava rock sometimes. But if we're talking about molten rock, magma's underground, lava's on the surface. There do actually tend to be some additional differences because lava's on the surface. That means dissolved gases, etc., tend to escape once it reaches the surface. So that can change some of the properties. Now, assuming the Earth was originally molten, which is a decent assumption, there's a good amount of evidence, then the first rocks on Earth were formed as the outer crust slowly solidified billions of years ago. So the very first rocks that ever formed were igneous rocks. And since these initial rocks were formed, geologic processes have modified, covered, and eroded most of these ancient materials. And it's estimated that about 80% of the Earth's crust is composed of igneous rocks, but about 75% of the continental surface, about 75% of the crust top layer is sedimentary rocks. Most of the igneous rocks are underground. But they're definitely relatively easy to reach in lots of places. So igneous rocks can be divided into two basic categories. There are extrusive igneous rocks that cool at the surface of the Earth. This is generally due to some type of volcanic eruption. The most common form of these are ocean floor called basalts. Basalt is an extrusive igneous rock formed from mafic lava. And the primary thing that makes up the ocean floor. There are also intrusive igneous rocks. These are igneous rocks that cooled somewhere beneath the surface of the Earth. So if you see when intrusive igneous rocks get revealed, they only get revealed due to some form of uplift. Something needs to push them up, and the overlying layers need to erode away. But the most common intrusive igneous rock is granite, which is a felsic igneous rock that forms at the surface. Underground. Intrusive igneous rock. So there's two types of igneous rocks. They're intrusive, they cool slowly beneath the Earth's surface, and extrusive, they cool quickly at the Earth's surface. And igneous rocks are classified according to two criteria. Their texture, which is generally referring to the size of the mineral grains or crystals in the igneous rock. Intrusive igneous rocks have large crystals, extrusive igneous rocks have small crystals. And then their mineral composition, the specific type of mineral crystals in the igneous rock. So the texture, the grain or crystal size of an igneous rock is determined primarily by the cooling rate of the magma or lava. If a magma cools very slowly deep within the Earth, large crystals form, such as within granite. If lava cools very rapidly at the surface, large crystals don't have sufficient time to form. You get a very fine-grained rock like basalt. And if lava cools extremely rapidly in water or ice, no crystals can form, resulting in a volcanic glass. It has to be very fast to get volcanic glass. So here's an example of granite rock in Yosemite, California. Plenty of granite out in the Rockies because they got pushed up and the overlying material got eroded away. So, intrusive rock cools at depth. The rate of cooling is slow, so the texture is coarse. An example is granite. Extrusive rock cools at the surface. The rate of cooling is rapid. The texture is fine. An example is basalt. And if it's extrusive that cools in the air or water very rapidly, you can glassy things like obsidian. Now, another way we can identify rocks is actually their color. Turns out the color of a rock is actually a pretty good indication to its composition. Because the amount of silica within a rock can be used to classify it according to its composition. Igneous rocks tend to either have lots of silica or less silica. So if the magma or lava is high in silica, minerals form with abundant silica, sodium, and potassium. These rocks are referred to as felsic. So intrusive felsic rocks are things like granite. Granite is an intrusive felsic rock. If the magma or lava is low in silica, minerals rich in iron, magnesium, and calcium that are formed that are dark in color, and these are referred to as mafic. Basalt is an extrusive mafic rock. So that is basalt. So just in general, the dark, low silica rocks are denser than the light, high silica rocks. Continental plates are primarily composed of less dense, high silica rocks and therefore stand high above sea level. Oceanic plates are composed of more dense, low silica rocks and therefore rests lower, usually below sea level. And if it's got medium density, it's called andesite, or medium silica content. That's the middle. So rock-wise, high silica content, this is called felsic. If it's extrusive, it will have small grains and a fine texture. It's called rhyolite. If it's intrusive, it will have larger grains and a coarse texture, called granite, primarily found in the continental crust. If it's medium, it'll be mostly dark. If it's extrusive, it's called andesite. That's small grains and fine temperature. Intrusive, with large grains and a coarse texture, that's called diorite. This is found in volcanic island arcs and continental mountain chains. And if it's low silica content, it'll be dark, extrusive with small grains and a fine texture, it's called basalt. If it's intrusive with large grains and a coarse texture, it's called gabbro. And that's primarily found in oceanic crust. So oceanic crust is denser, more mafic. Continental crust is less dense and thicker, and it's got more felsic rocks. Okay, so I think I will stop here. That is the place I was going to stop anyways. Just unhide this. So we have a lab today. Stop sharing.